Alright, in this video we're going to talk about the conservation of energy, and the main idea there is that the total mechanical that we start with is going to equal the total mechanical that we end with at any 2 points in the object's motion. Alright, if energy is not conserved, that means that the final total mechanical will be less than the initial, so some of it had to have gone into something else, like friction. But most of the time, it's going to be zero for this video. Alright, so a ball is dropped from 10 meters above the ground. The ball has a mass of 2 kilograms. Using conservation of energy, we want to figure out how fast it's traveling just as it hits the ground. Okay, so starting with our law of conservation of energy, mechanical energy is either kinetic, spring potential, or gravitational potential. All right, so if we look at the situation, the ball is dropped from some height before it hits the ground. So is it moving? No. Does it have a height? Yes. Is there a spring? No. So we only have gravitational potential energy. So mgh naught. Now that has to equal whatever's at the end. So at the very end, once it reaches down here, does it have a height? No, it's just about reaching the surface. Is it moving? Yes, that's when it's moving its fastest. Is there a spring? No. So the only thing we have at the end is 1/2 m v squared. Now if we look at both sides of the equation here, we can see, hey, mass crosses out. It's going to cancel. So it doesn't matter the mass of the object. So in the second question, the answer is this going to be the same as what it is for the first one. Solve for the speed. All right, so we have 2 g h naught. So that's multiplying the 2 over. And that's going to equal v squared. So I'm going to square root both sides. And we get an answer of 14. Meters per second. All right, so it's a nice simple problem. Only one form of energy on each side. Excuse me. All right, so let's look at another one. All right, now here we have a block that's pressed against a spring. So the spring would usually be in its relaxed state here. So we're exerting a force and pushing it back from this location and holding it there. Okay. So we want to know how fast will the block move after the spring decompresses. So we're going to release the block and spring, and the spring is going to shoot the block across the surface. Okay. Start with our conservation of energy equation. There's no friction, so we don't have to add that work. We know that whatever it ends up with is whatever it started with. All right. So at the beginning, is it moving? No. Does it have a height? No. Is there a spring? Yes. So we have the spring potential, which is 1/2 kx squared. And after the block is released from the spring, no more spring, still doesn't have a height, but the block is moving, so then all of the spring energy is going to be turned into kinetic. All right, looking for the speed. On both sides of the equation, there's 1/2, so we can get rid of that. There's no mass on the left-hand side, so here the mass is going to matter. Okay, so we're solving for speed, so I have to divide kx squared by the mass. and then take the square root of everything there. If we plug everything in, we'll get 2 meters per second. So the second question is, what happens if the mass on the bottom is twice as much? Right. So just using your calculator, just plug in 2 kilograms on the bottom there instead. Right. So 0.2 squared is 0.04. Multiply that by 100. We get the 4. So when we divided that by 1 and square root it, we just got our 2 meters per second. But now we're going to divide that by 2, and we get the square root of 2. So when the mass is doubled, it'll decrease, and that should make sense. It's harder to accelerate a larger mass. So the spring will still be exerting the same force, just on a different mass, different acceleration, different ending speed. Okay, let's look at a roller coaster type of problem, and in this problem we're going to have more than one form of energy on each side of the equation. It's still conservation of energy. It does say at point B it is moving, and it does have a height with respect to the bottom of the roller coaster. And we want to know how fast it has to be moving here in order to make it up to that top of this hill with that speed. Okay, this one also has a height. So starting with the total amount of energy at point A, that has to equal the total amount of energy at point B. At point A, does it have a height? Yes. So there is mgh. Is it moving? Has to be moving. If it's not moving, it won't go down the hill. So 1/2 m squared at A. And there's no spring. And then we look at point B. Object does have a height. And it is moving. Now, looking at each side, we can see that everything includes the mass of the roller coaster. Another thing you might have noticed is it didn't tell us the mass of the roller coaster. So, all of those are going to cancel each other out. We're going to look for the velocity. Now, when you have this long equation, what might help simplify it so that the algebra is a little easier is multiply each term by 2 and write out what that's going to be in the next step. So we'll have 2gh plus va squared, because that 2 and that 2 cancel, is equal to 2ghb plus vb squared. This is the one we want to look for, so we just move everything to the other side. Okay, now this is 2ghb, but we're going to subtract 2gha. So what's the same in both of those is the 2g. So we can just take those changes in heights and subtract them. And then add the square of the speed at vb. So this part here is really just the change in potential energy between the points. Okay. So if that's the height at point A, that's the height at point B, that is HB minus HA. might be an easier way to see it. So it doesn't matter what this roller coaster does, it just matters the change in the positions vertically when there's no friction. And I forgot my square root of all that because that's supposed to be VA squared. All right, so let's plug in our numbers and see what we get. And you should get 17.2 meters per second, not meters per second squared. All right, we still got more to go. So let's try another one. Now we're going through loops. All right, so this is saying the first hill in a roller coaster is 38 meters high. So there is a starting point here. And it tells us the mass of the roller coaster. We want to know if it'll make it around the loop if it has a radius of 15 meters. All right, so this is 15 meters. This is point B, this is point A, and that is point C. Okay, in order to make it around the loop, the roller coaster has to be moving at this point. And if we're checking to make sure that it actually makes it around the loop, we would have to know the minimum speed needed to go around that loop. So we're going to bring in our circular motion into this. So we know that the V at this point has to at least equal G times R. So this is going to be a comparison. We're going to solve for how fast the roller coaster is moving at point B, and then plugging in G times R to figure out what the minimum speed is going to be. All right. So this will be h naught, the starting height. So our initial energy at the starting point has to equal the energy at point B. At the beginning, when we talk about roller coasters, the first hill, old school roller coasters, they just kind of like have that little track that pulls you up the hill, and you very slowly go over that hill. We're going to estimate that the starting velocity is going to be 0. So the velocity at that point right here is 0. So is it moving? No. Does it have a height? Yes. Is there a spring? No. So this total energy that we start with is just mgh naught. When it's at the top of the loop, is it moving? Yes. Does it have a height? Yes. That height is going to be twice the radius. All right. And that's it. Let's figure out how fast it's moving at the top. Mass cancels. Multiply everything by 2. All right, we get that. Subtract this over, and we're really just going to get the change in potential energy, which would be the difference from this height to that height. And that's what's going to affect how fast the roller coaster is going to be moving. So 2g h naught minus hb is going to be equal to vb squared, so we're going to square root that. All right, square root of 2g, 38 meters minus 30 meters. we get 12.5 meters per second. Now, if we compare that to the minimum speed, which is the square root of GR, we get G times 15 meters, and that'll be 12.12 meters per second. So the roller coaster will go through the loop since it is larger than the minimum needed to go around that loop safely. Okay, you might have been able to see it if you compare these two parts of the equation right there. This is going to be equal to the square root of G times 2 times 8, which is 16 meters, where that is a larger value than G times 15 meters, right? So since this number will be larger than this number, it means it does have enough speed to go around. Okay, the next part of this problem is how fast is it moving when it gets to point C? So after it falls halfway down through that loop. So it's basically a brand new problem. I have to start over. Okay. And the thing is, you can pick any 2 points. You can actually state the energy at point A and compare it to point C. The energy at point B and make it equal to point C. As a starting point, a standard, I always use the starting point of the roller coaster. All right, so the energy that we start with has to equal the total energy at point C. We're starting with just potential. At point C, it is moving, and it still has a height. And that height would have to be equal to the radius of the loop. All right, so just solving for VC. It should move faster, right? Because as an object rolls downhill, it's going to increase in speed. So we should get a larger speed than what we got at point B. Okay. Manipulate the equation again, multiply everything by 2 if you like that method. Okay, masses will cancel as well. So far, the masses have canceled as long as there wasn't a spring. Okay, and if you keep working through without numbers, you start to see this very familiar equation here, which actually relates to kinematics. In that equation, right? So if we square root that, square goes away here. In this situation, our velocity at the top was 0. So we have the square root of 2a delta x or delta y, whatever you're doing. So in this case, it would be 2, acceleration is g, and the delta y would be the changes in the heights. So you can see that that equation relates exactly to this. And we get 20.3 meters per second. So it's larger than what it was at point B, so we're on the right track. It gives you something to be like, oh, okay, I probably did it right. The speed makes sense. All right, just one more example, and it's using no numbers. All right, so we have that roller coaster here, and this does have a certain radius that has a starting height, and we want to know what this has to be for the car to go around the loop of any radius. So it's going to be how many times r does the height have to be? All right, so what we're really going to get is an answer of h has to equal some number times r. So we're trying to figure out what is that number there that we have to multiply the radius by to figure out the starting height. Okay. It's still conservation of energy. The starting energy has to equal the final energy. Our final energy is at point B, the top of the loop. So when we start out, it would be just releasing the car at rest. So we only have mgh. At the top of the loop, we still have that height, and we still have to have that minimum speed. Pay attention to this. You will have to solve this type of problem on your own. All right, nice thing is m's cancel. We are looking for h. We can still do the multiplying by 2 to cancel out that 1/2. And we end up with 2gh equals 2ghb. But what does that height at point B have to equal in terms of the radius? So we're assuming this loop is a perfect circle. All right, so radius is half of the diameter. So the height at point B would be 2 times the radius. So I'm going to substitute that in for HB, 2 times the radius. Plus v squared. The next thing we have to make sure that we include is that that speed at the highest point is the minimum speed. All right, so notice I just got the potential energy in terms of our radius of our loop. So now we're going to get the speed in terms of the radius of our loop. Because we know that Vmin is the square root of gr. We're squaring that. So the square of a square root here would just be gr. So now that we have the same variable in both those terms, we can just add those two together. So 2gh equals 5 gr. One more step is solving that for h. G is on each side, those will cancel. So the height has to be 5/2 of the radius. So for any roller coaster to go around the loop safely, this would be the minimum height needed for that first hill. If you don't have that height in relationship to the radius of the loop that you want to go through, it will not go through that loop. All right? So if the radius of that loop was 10 meters, right, you would have to start with the hill that was at least 25 meters high. All right? So make sure you understand the substitutions that were made, which are that the height of the loop is twice the radius, and that the speed at point B is that minimum speed, which is the square root of gr squared. All right. So that's really what energy conservation problems are going to look like. It makes more sense seeing many examples rather than just saying, hey, the energy here equals the energy here. Always ask yourself those three questions. Is it moving? Does it have a height? Is there a spring? And that sets up what's on each side of the equation. And again, you're always just picking 2 points at a time to compare. Well, I hope this helps, and it's time to practice.